All right, welcome everyone. It's noon and we can get started with another edition of VQMS. We're very, very happy to have Bryan Bollinger with us today talking about solar subsidies. A few housekeeping things before we get started. We have a great panelist, a set of panelists here. So if you are one of the panelists, please just unmute yourselves if you want to ask questions, just as in a typical seminar. Others, if you're in the audience, please use the Q&A feature to ask questions, and we'll try to ask Bryan your question when there's a break. And then we're planning to go for about an hour until 1 p.m., including questions, and then we'll stick around for another 10-15 minutes or so if people want to have a more informal discussion. With that, again, Bryan, welcome. The floor is yours.
Thanks, Raluca. Thank you all for attending today. I'm really looking forward to getting some feedback on a project which we've been working on for longer than I probably should admit. This is work with Ken Gillingham, who's at Yale, an economist, and then Justin Kirkpatrick, who's an economist at Michigan State, who was a former PhD student of ours at Duke. It's called Valuing Solar Subsidies, and essentially in this paper, we wanted to estimate the trade-off that consumers have between the upfront costs of installing a durable product like solar with the benefits. And this is a nice category because there's this clear flow of benefits that accrues over time, and we know where the bulk of those benefits are occurring. It's through the offset costs of grid electricity. And that benefit stream is then, traded off for the upfront costs of actually putting solar panels on your house. And a lot of these green technologies you see, whether it's solar or electric vehicles, have this kind of trade-offs. Some upfront cost or additional cost for that durable good, but you also get a more sizable flow payment as well. So in terms of discounting, this is obviously a really long literature. There's been a lot of experimental work looking at not just discount rates, but the discount function as well, moving beyond just exponential discounting. We will use exponential discounting in our structural model. There's been field experimental work as well, looking at the degree to which consumers trade off a payment today versus a payment at a future date, and then observational work as well. We can go back to Hausman's environmental econ paper, which was looking at the decision to buy more efficient washing machines. And that paper found pretty high implicit discount rates for this example of an energy using durable. In that paper, a lot of structural assumptions were needed in terms of policies being known, not changing, the stream of utility benefits also being the same over time. And since then, there's been a lot more work thinking more about the identification of discount rates without those strong assumptions, and even a little bit of work looking at heterogeneity in discount rates, going back to Lawrence in '91 and Harrison et al. In 2002. Right now, there's a huge policy debate around the idea of net metering. And essentially, the way this benefit works is if you put solar on your roof in most US states, you actually get to roll back your meter, which that video was trying to show. So here, let me show it again. So you're feeding in electricity, it's dialing back the meter, and now it's nighttime and you're running it forward. So what this essentially means is that consumers are able to feed in their solar electricity to the grid and get compensated at the retail rate. Not surprisingly, utilities don't love this policy because they could have bought that electricity at a wholesale rate, which is much lower than the retail rate. It also has challenges in states like California who use tiered electricity pricing, where when you consume a higher total amount within your month or your year, it shifts you to a higher price point. So this is a fairly aggressive policy as well, essentially compensating consumers who are consuming at a higher price tier, i.e. they consume more than the exact same electricity coming from a solar installation for someone who consumes at a lower price tier. The debate across the US right now is whether we should change these rates where the incentive essentially is closer to the marginal cost of generating the electricity, which would have been paid to some other generating facility. This map shows you the states which have net metering. It's the bulk of the US as well right now. The green states are ones that use something other than net metering. It's only 8 states right now, and 2 states are in transition. But the bulk of the US, again, does use net metering. If I'd given this talk 5 years ago, it would have been everyone. We wonder whether this is actually a second best or third best policy even for solar adopters. So there is an indirect benefit of installing solar in the reduction of externalities caused by air pollution and greenhouse gases. Perhaps net metering could also lead to some benefits of learning by doing. There's other ways you can increase adoption rates, of course, as well. And potentially these types of incentives could induce some innovation. But really, how much you value a policy like net energy metering completely depends on the discount rates that households have. And I should say implicit discount rates, because it's going to capture more than just time preferences. And one thing that we're going to show is that there's actually substantial heterogeneity in these discount rates across consumers of different wealth bins. So the main research questions are, how do households discount the future payoffs from rooftop solar? This is going to speak to the economic efficiency of any similar type flow subsidy. We also are going to, again, assess whether discount rates systematically vary by wealth, which speaks to the concern about equity. One of the things that we hear all the time is that solar subsidies are subsidies for the rich, because we disproportionately see higher wealth consumers adopting solar than lower wealth consumers. And differences in discount rates are one reason why we might see this. The policy lever, of course, that you could change, you put the subsidy up front, or more of the subsidy up front, rather than it having essentially an artificially high flow subsidy, which is what we have now with the NEM benefit. There's quite a bit of a literature on solar subsidies. You kind of have to start with Olivier's paper with Frank Verboven from 2019 in the AER, I believe. They found a 15% implicit discount rate using a dynamic structural model. Here, the key identification was looking at variation in panel costs and subsidies over time. And a lot of papers who've tried to estimate discount rates use this type of variation, where there's a policy shock which changes that benefit, tomorrow or some future date versus today. I use the same type of identification strategy in my job market paper on dry cleaning firms. You've seen it in some other papers in the energy using durable space. Again, the bulk of papers who've been able to identify implicit discount rates are using this type of strategy. We're going to use a slightly different strategy. I should say here, we're going to focus a little bit more on cross-sectional variation. So we're still going to have to use some assumptions about future expectations of consumers, but we're not going to depend quite as heavily on them. To think intuitively, the type of identification we're going to use, let's say Wes Hartman has a great sunny roof. I have a shady roof, but aside from that, we're the same, right? Blonde hair, big foreheads. We're leaning back in our chairs right now. So we're identical on every characteristic other than the amount of sunlight we get. Typically, consumers offset their full energy bill. So means is that I have to put more solar panels on my roof to get the same flow benefit that Wes gets. So in that example, we get the exact same flow benefit, but I have a higher upfront cost because of my shadier roof. And that's the type of variation we're going to use in this paper to identify discount rates, to see how much more is Wes likely to adopt solar in comparison to me. So again, we may need to make these assumptions about future expectations, but we're not going to be quite as reliant on them. I should say that the implicit discount rates that we're going to estimate in this paper, they do differ from time preferences. So they can capture time preferences, but they can capture other things as well. Cullen Williams, 1999, sort of point out that this real rate of return like where consumers are indifferent between payments today and tomorrow, that will only equal a consumer's discount rate if it lies between their borrowing and lending costs. So one reason why we find that discount rates are going to be higher for lower wealth consumers could simply be differences in borrowing and lending costs. There are other reasons as well for that difference. If there's a difference in the marginal propensity to consume income as you get it, that can actually lead to a difference as well, because lower wealth consumers value upfront money more because it gives them the ability to smooth their consumption. So that's another factor. And it turns out that that ability to smooth is going to be valued more than by those lower wealth consumers. Differences in risk aversion can also lead to differences in this implicit discount rate. And there's an interaction between risk aversion with your background consumption. Background consumption levels are usually ignored when estimating these discount rates. But because of this interaction effect, it could be that lower wealth consumers who have lower levels of background consumption, even with the same risk aversion as higher wealth consumers, that will lead to an implicit discount rate being higher. This is the general outline of the talk moving forward. I'm going to talk about the data, again, highlight the identification strategy, spend a little bit of time on the structural model, and then show you some of our preliminary results and counterfactuals. So these are what the data look like. We have address level data on solar adopters from Lawrence Berkeley National Lab. This has the costs, the system sizes, the exact date of installation, whether it's a lease or purchase system. We also have address level data on solar potential from Google Sunroof, which essentially gives you how yellow each of those rooftops are. It's the generating potential of any specific area on your roof. And in addition to this, we know not only how much sunlight hits that roof, but what the offset grid price would be as well. It's data that Google collects in the background. So the empirical setting is going to be California. We're going to look between 2014 and 2016. Again, we're going to take this address level data on all owner-occupied homes. We have the latitude and longitude from geocoding, things like square footage, stories, the year built. This is a base data set from CoreLogic. Wealth data we get from Info USA. And we also have voting registration data, whether you're an owner, children, length of residence, things like that as well, also from Info USA. We combine this data with utility data from PG&E, and that's one of the reasons why this project got delayed, because it took a while to, one, get the data, and then it also took quite a while to get them to approve our security measures to protect the data. But this gives us actual consumption for solar adopters. We also have household consumption data for all the non-adopters, but we don't know which household is which. So we're essentially going to use the distribution of consumption within the zip code and integrate over the unobserved dimension of heterogeneity, which adds a layer of complication because unlike standard simulation methods where you're drawing with replacement, here you would have to draw from the empirical distribution without replacement, because otherwise we would predict all non-adoption by people who don't consume any electricity and have zero value of solar. So you essentially have to add a constraint that it sort of sums up to the empirical distribution within that zip. To do that, we're going to calculate these quintiles without an I noticed right now of non-adopter consumption once we remove the adopters.
Hey,
and then, of course,
Brian,
electricity rates as well. Yeah.
I want to ask you a question just about the kind of the previous slide with the yellow roof. So this is going to be kind of the key feature in here. And is the idea that everybody should kind of be able to get or know that whether they've got a good roof or a bad roof, et cetera? Is this going to be a critical assumption? And it kind of makes me wonder, is there a way to look at, search, Google Trends or search traffic to see, are there systematic differences across demographic groups and who's kind of getting access to that information of the potential viability of solar at their location?
Yeah, we haven't looked at Google Trends. It's a great point. We are going to assume that people know things like the break-even time, how much generation they're expected to get for their household. We didn't want to look at Google Trends data on this website specifically, although it is a really easy website to use. I encourage you to type in your address, see how much money you'd make from solar. Even when consumers aren't using Google Sunroof, though, installers will go out and do a site visit, and they will do their own estimates, looking at the obstructions nearby, and won't be quite as accurate as Google Sunroof. But there were a few other online tools as well that came up, which allowed installers to assess, how much you would get from generation. Going back, well over a decade, we had data from Lawrence Berkeley National Labs on the expected generation for households. So we haven't looked at Google Trends. It's a nice idea. I worry that it wouldn't be a great representation of whether consumers have that information, since installers were providing kind of a rougher proxy of that information even before Google Sunroof was around. But
yeah, I guess maybe connected to that, you start to just wonder, like, are different types of groups going to have different access to the installers, or the likelihood of having them come out there, et cetera? And is there any reason why we should think that there is, or there's not any such systematic differences about getting access to that information?
It's a good point. I have to think a little bit more about, you've probably all been pushed display ads for solar in your area. Installers, you always get a home visit if you go down the purchase funnel. We haven't heard stories of consumers who wanted to get solar or were interested who couldn't get a site visit. But awareness of the value is something that we should think about more.
Bryan, maybe a related point. So in this industry, how much supplier targeting is going on? So if I'm a supplier of the solar panel, I would look at this data and I think, okay, VES has a better roof, so therefore I should better target that block instead of the block that have a worse roof. So there's a different set of information provision just because of the condition, and those who get targeted more end up adopting more.
Yes, so there's going to be more value to the consumer if you have a sunnier roof. And some of the lease systems, obviously, where the solar installer is paying to put the panels on your roof, and you have a power purchase agreement where you're buying the electricity from them, the value of a sunnier roof is going to be higher for the solar installer as well. There's not evidence that we could find on sort of micro targeting where I'm going to go up and target Wes because he has the sunny roof, but I'm not going to target you because you have a more shady roof. Once you're in the neighborhood, there are some economies of scale. One of the questions we would get when we were working on our effective visibility in durable product adoption paper that just came out of Marketing Science was whether you sort of had targeting of neighbors once an installer was, in your cul-de-sac or whatever, which is something that is a very real possibility because you get economies of scale once you already have your trucks and the panels out there. So no evidence at all. And I just actually got back from an installer with sort of 75 solar principals at different companies. No evidence in terms of targeting one household because they have a sunny roof, but not the one right next to them who has a more shady roof. And that's the kind of variation we're using here.
Bryan, there's also a question from the audience from Avery, who's asking whether households can increase the amount of sun that their roof gets by, for example, cutting down trees, or should we think about this as sort of a constant feature of the house?
It's a great question. It's two things. Actually, give me a second. I'm going to address that identification challenge in just a few slides, if that's okay, Avery.
Sounds good.
First, I wanted to talk about what we're going to observe for the solar adopters. We actually get to see their size. How we're going to deal with non-adopters is that we are going to essentially create a sizing model. We're going to use a sizing model actually for everyone because we are trying to figure out the value of solar, which determines on how big your sized installation is going to be. So if you think about what we need to think about, we're going to have some houses who just have a ton of sunlight, and you're going to install solar panels up until you have offset your full consumption. One of the unusual restrictions on net energy metering is that you get hardly any compensation for oversizing your installation. So what I've drawn here It's a comparison of the cost of solar electricity generation given by these sort of smooth curves and the marginal cost for grid electricity you would face per month. And this is a simple two-tiered pricing structure where you would, the first tier for electricity prices is 15 cents and then it jumps up to 25. So if I'm consuming electricity at 25 cents per kilowatt hour, right, that is my offset price when I make an installation. So in that case, it could be that I want to offset my full consumption. It could be that I just want to offset my consumption until I drop down to a lower price tier. So this dark blue curve here, this is someone who has a shady roof. The marginal cost of solar is almost 30 cents per kilowatt hour. If you look at the levelized cost, I'm not going to adopt because that's more expensive than grid electricity, unless I get some other, intercept value from solar. In terms of the yellow roof, this is someone who has some nice shade, sunny spots of their roof, but then the profile drops rapidly after that. So a nice little sunny patch and then a lot of shade. So the marginal cost starts down at 10 cents per kilowatt hour, increases rapidly, and then I'm going to stop installing once I reach the point at which the marginal cost of solar electricity is 25 cents, just like the grid electricity. This purple example is someone who has a lower marginal cost of solar electricity up until they consume enough electricity to push them to the lower price tier. And now because their marginal cost of grid electricity drops from 25 cents down to 15 cents, they stop. Green is someone where they are offsetting even at the lower tier up to a certain point where the marginal cost equals the marginal benefit. And this light blue curve on the bottom is Wes with all that great sunlight, who has a lower levelized cost of installing solar all the way until he offsets his full consumption. So we have to add the sizing model to figure out what you would install before we can then estimate the adoption decision. These are 3 examples within our data showing you this. It's 3 systems, are in different zip codes, they have different rate structures. Most of the price variation we have is actually when the tiers move, not the actual level of the tier. So this orange curve would be someone with a really shady roof. So the levelized cost, again, is quite high. Blue is in the middle, and gray is someone who has a really nice roof for solar, who would then install more solar panels. You can see the crossing point right where my hand is. So in terms of identifying discount rates, we're going to need the variation that affects this expected discount of future payoffs without affecting current period utility. We're using the strategy I already said, and you can think of that. It's really it's affecting the relative expected discount payoffs versus the relative upfront payments. So we are going to use variation in electricity rates. We're going to use variation in rates not just over time but across zip codes. We're going to look at variation in consumption levels over households from our PG&E data, and then variation in the potential generation from the Google sunroof data, which again is some of the key identifying variation coming from that.
So Bryan, I have a question. So you're really going to focus on the discount rates and look at the heterogeneity across these wealth levels. I wonder, to what extent is it like, have you thought about other components of the net present value varying across these wealth levels? So for instance, I'm thinking like somebody at a lower wealth level might have, the budget constraint might bind more quickly. They might not be able to make the investment. Or on the other hand, if there's any correlation with the time that they expect to spend in their home, for instance, and maybe they don't recover all the flow payoffs that somebody else might. And so I guess, like, is it the discount rate, or are there potentially heterogeneity on these other elements for the net present value that might be important?
Yeah, we're going to allow for lots of components of heterogeneity within the intercept term. In terms of heterogeneity within sort of the economic value of offsetting your grid costs, we are capturing that through the implicit discount rate. So if there are differences in the cost of borrowing, that's being captured in the implicit discount rate. If there's differences in the expected time that you're going to move, there is evidence that a purchase solar installation is a large bulk of it's captured in the value of your home when you sell it. It's not 100%. So the decline in that value, that would also be captured in our discount rate. So there are some extra things in there as well.
I guess for like the, yeah, I guess like for how much of it is captured through resale value, like you could take a look at, presumably you have the address, you have the resale values, you also have the propensity to move, right? Like how quickly how long they spend in the house. So you could use some of those data to actually get at that.
Yeah, and we're actually going to use the propensity move to deal with one of the identification concerns, sorting. We don't know when they're going to move again or what their expectations are for moving again. So right now we're captured in the discount rate. We've tried decomposing the discount rate a little bit based on things like lines of credit. We haven't done it on other variables yet. For the price variation, we're going to use these climate zone differences, and essentially you have differences in prices across these zones. Sometimes it's the level of the price tier, more often than not, it's the cutoff of the price tier, but that still gives us the identifying variation we need. And we're going to focus on the zip codes that lie right along this border to give us that difference in the value of the offset electricity. This is an example where you sort of see these sort of colored in zips right on the border on one side and the sort of the white filled ones on the right. So our final sample is going to have about 300,000 households, 7,000 of which capture electricity. This figure shows the intertemporal variation in electric rates over time. The highest tier, you actually see a slight decline for a while before it goes up. Tier 3 declines and then jumps. The reason for this is essentially so few people fall in tier 3, they were shrinking the size of that tier that they actually did away with it at the end of our panel. And that's why you sort of see this weird pattern. And electricity rates are actually climbing the highest rate for the second tier of consumers. And we have tested it with expectations on average and also by tier, and our main specification uses expectations on how electricity rates increase at the tier level. This gets us back to that variation in the upfront cost versus the value of the stream of benefits from offsetting your grid consumption. So this is not California, this is actually Michigan. This top house is Justin, and he was comparing it to one of his colleagues, where one of them has a lot of shade, and one of them has this nice sunny patch on their roof. Now, one of the identification concerns that came up is the fact that you might be able to chop down a tree, let's say, or some limbs, and make this a little sunnier. So we don't have a great way of dealing with this concern. It's a little less troublesome in California, where a lot of the trees that are near the more urban areas we're looking at are shorter trees and often are on your neighbor's property. We talked to an installer out there who said, optimally, you should never have to, chop down trees in order to make room for solar. But it's something that we can't really deal with well. Chopping down trees would be another upfront cost, however costly it is to you to chop down trees or limbs. And then we would see, you would have a sunnier roof if you did it. So what happens is for non-adopters, you clearly thought that the fixed cost of chopping down limbs or a tree was higher than the expected benefit of the slightly sunnier roof. For solar adopters, we're going to see them after they chop down those branches. So we're going to see the sunnier roof. So I'd love thoughts about how that might change our estimates of discount rates. We don't think it's common at all, but it is something that we need to address in the paper. The other thing that we are addressing is concerns about sorting. You didn't see a lot of households selecting homes because they were well suited for solar back in 2014 to 2016. It is possible. We do have boundary fixed effects to try to deal with those issues, which we think help quite a bit. And we're doing a robustness check in which we exclude people who moved recently as well, who might have sorted in that fashion. Was there a question, Wes?
Yeah, Brian, So you've kind of talked about two sources of variation here. One is this one here, which is, if I'm following correctly, this is kind of what's affecting your immediate costs of installation. And then you just previously mentioned this kind of border aspect in these prices. Is the idea that you're going to hope that these are kind of two different sources of exogenous variation, one shifting prices today and another one shifting kind of long run aspects together to try to help you get this? Is that the logic? And then just to follow up, once you kind of get in that border area, a number of concerns can come up with these estimators. Any thoughts about those? Or we think things are fine in this case?
Yeah, I mean, most of these borders are, I mean, it's not running through a city, obviously. They're borders because they're climate zones. So the idea is that the average climate, if going back to your paper, but so the average value, like over a large geography, right? You know, like the San Francisco Bay is considered different from once you kind of cross the mountains and you're the other side in the Central Valley. But along the border, the houses seem to be in a similar climate. So if you look at where these border zips are, we weren't too concerned about things like a big discrepancy between, let's say, air conditioning needs for a zip right to the left of the border versus right to the right. I think those are the types of concerns one might be worried about. We did want both sources of identifying variation. Let's hypothetically go with a situation in which we're offsetting full consumption again. So in that case, when, you know, Wes, you have your sunny roof, I have my shady roof, I have to put more panels on than you. That gives me some really nice variation in the upfront costs to offset our full consumption. If I can combine that with differences in, you know, electricity rates, which are offset, that gives me also then variation in the stream of benefits in the future. We're going to convert all of this value that consumers get into actual dollar values. So we wanted to be able to pin down, you know, utils in dollar terms rather than just having it in sort of scalable utils.
Mm-hmm. I mean, I guess just to kind of a couple other things that come up. Like sometimes we worried that these borders are in weird places, which in some cases means literally nobody's there. Now you have, I think, pretty small regions and zip codes that you should be able to find that. But do we think that these people might be systematically different from kind of the average population and coming out and affecting things that way? Like oftentimes these borders aren't chopping right through the, you know, regions of metropolitan areas where the vast majority of the population is sitting. Just curious. Yeah,
I mean, some of these are through pretty urban areas. It is just the PG and E area up in the, you know, the northern sort of central area here. We haven't really thought that much about how representative these border households are to all households in the zip. It's a table that we should do for generalizability.
So Bryan, maybe one more question. So you talked about sorting, really about people trying to buy a certain house because they want to put a solar panel on top of it, and that would be an issue. And I can see maybe that's indeed not going to be a big concern. But how about sort of other variables that might be correlated with both? Think of people with strong environmental preferences might want to live in a place with a lot of trees around it. That's going to create a shadow. Would that be a concern here?
I don't think it will be a concern, but only because of the kind of robust set of controls and fixed effects that we're going to use in the regression. So we're going to allow for a lot of heterogeneity that shifts that intercept for solar. So differences in environmental preferences that vary with like how shady, let's say, this region is versus that will be accounted for by these fixed effects. And so we're going to be looking within this little region, you know, this house happened to be shady and your next door neighbor happened to not be shady. So I think we're going to be okay that given the amount of fixed effects we're going to use and other controls.
Yeah, so both individual controls and local fixed effects, you say, because it could still be that I have a garden with a lot of trees and my neighbor doesn't.
Yeah,
because I like trees or because I'm an environmentalist.
So we're going to use, at the individual level, sort of the set of variables. Let me go back here. Things, you know, we're looking at owner-occupied homes. We're going to look at the length of residence, children, voting registration. We think is going to capture some of these environmental preferences as well. Things like square footage of your house, year built. We have age in there as well. So we are going to use some household level controls as well to try to make sure we are comparing apples to apples. when we have this sort of sunny roof versus non-sunny roof comparison.
Okay, thanks.
For these two example roofs, again, this is sort of Justin and his colleague. These are their different profiles. So again, this is the marginal annual generation per panel. So for that sunny roof, it's a much higher generation levels. You can see in this profile, you get lots of sun, lots of sun, lots of sun. It drops off a bit then, versus this one where the sunniest spot on the roof is barely better than kind of the shady part on that first household. And this type of difference in the expected generation per panel maps straight onto the levelized marginal cost per unit of solar electricity being created on the right. Whereas this really sunny roof has a really low levelized cost for electricity versus this high cost for the person who has a shadier roof. In terms of some basic model-free evidence that we might see discount rates that differ by wealth bin, I want to show these graphs where we're looking at the share of people adopting solar as a function of your per period payoff from solar. So think of this as someone with a shady roof, kind of middle roof versus a sunny roof. And on the left, we looked at people who are within $500 of the median total cost of installing. And then on the right, within $1,000 of the median total cost of installing, because there are some differences in the cost of installing. So this is just how big the bin is. Let's focus on the right. They tell the same story. Here you can see for a low wealth consumer, as you go from a shady roof to a less shady roof, the probability of adopting hardly changes at all. It goes up some if you start to get to a really sunny roof, but this slope still is a lot less steep than you see for these middle and high wealth consumers who are clearly responding a lot more to a changing flow benefit as you go from a shady to a sunny roof than these lower wealth households. And that difference in the slopes between these curves is what's really going to identify the differences in discount rates for the wealthy households versus the non-wealthy households.
Just a clarification. So how wealthy are the low wealth households?
We should have that. I was just looking at the paper today to find out what the average wealth was per bin, and I couldn't find it. So we have to go and run the stats again. I'm sorry. These are owner-occupied homes in California, so we have to sort of take it with a grain of salt. We looked at this by income as well at first, but there are too many retirees who report as low income. So we thought the wealth measure was a lot better. I don't have that off the top of my head. I'm sorry, Christina.
No worries.
In terms of the structural model, it's going to look a lot like Olivier's AER paper from 2019. Consumers are going to make, essentially a decision of whether to adopt solar or wait. Adopting is an absorbing state. If you don't adopt, you get the chance to adopt in the next period. We're going to have consumers consider their upfront costs and the discounted flow of payoffs. And the value of waiting is going to depend on your state variables. These state variables could differ by solar radiance. And again, consumers are essentially making this trade-off between the flow benefit and the upfront costs. The value of waiting will depend on your expectations of how electricity prices and solar prices are changing. So we do have to build in some estimates on how those expectations evolve. And then we're going to estimate discount rates as a function of wealth.
Bryan, sorry, just to kind of go back a little bit. How much does the consumer sophistication come in here, in the sense that they have full awareness of, the benefit, the cost, and how that level of understanding may vary across different consumer wealth status?
I think it relates back to Wes's question about how much people might use a tool like Google Sunroof. California at this point was a much more mature solar market than the rest of the US. So I know it's still sort of early days of solar in the US between 2014 and 2016, but the California Solar Initiative had already been, spent down at that point. So California was way ahead of us at this time. There are lots of solar installers, and they really market solar a lot, especially in California. So lack of information wasn't a first order concern for us. because you have installers coming out and saying, hey, look, you have a great roof profile. Your payback period would probably be this many years. There could be differences. It wasn't, again, a first order concern for us. But if there was, we are hoping that those differences would be captured through the intercepts in terms of your overall propensity to adopt, which is independent of your propensity to adopt as a function of your household irradiance. It's one reason why we're actually going to include things like wealth as well within the intercept, because we don't want to force things like wealth to act only through that long-term value of installing. We want to make sure that if there are baseline differences as a function of wealth, we are capturing that as well through that intercept term.
Bryan, just to follow up on that, so also there's sophistication about knowing the current policy, but also about the expectations about the future, right? So you said that net metering was abolished in certain states in the US. I mean, it used to be more than now. So is there any concern there?
Yeah, so we're only doing this with California data, where you don't have a change in that policy. We actually assume that consumers aren't super sophisticated in their expectations. So actually, I'm going to show what the assumptions are regarding dynamics right now. We're going to assume kind of the standard, right, panel generation decline by 0.8% per year. I can't remember. I think this is a number you used as well for the quality of the panels themselves. It's a really small amount per year, but we incorporate that. We assume that consumers believe electricity rates to be following an AR1 process. And we're going to do this by each of the 5 tiers. We actually do an even more simple version than pure AR1 because we estimate the AR1 process, and then we assume that consumers believe that it follows that path deterministically. Now, if you add an error term, again, like Olivier's paper, you can show that that error term can drop out under some assumptions. But we're going to assume pretty simplistic ideas of how things like electricity rates evolve. So we estimate the electricity rate with this AR1. The value, again, is going to depend on what consumption bin you're in. We're also going to assume that solar panel cost decline are AR1 as well. And we're going to put the cost decline on the variable cost of installing, not the fixed cost. There's sort of a set cost of driving your trucks out and setting up shop, and then the cost sort of per panel. And if you look at the data, it looks like the declines are through that variable cost, not through the fixed cost. So that's where we put the AR1 process for the solar costs as well. This function then gives you the utility of adopting. So this green term is the discounted value of offset electricity, right? You're just summing up from time equals 1 to capital T. That's the life of the panel. We use 25 years as the working life of a panel. Delta is the discount rate. You're going to discount PT. PT is going to be the price, the average price of your offset electricity term. And the integration is over your bounds from Q naught minus Q star. Q naught is how much you are consuming electricity before installing. Q star is your optimally sized solar installation in terms of how much generation you get. So this bounds of integration allows you to offset, again, the cost of the offset grid electricity you would have consumed if you didn't install solar. And many people just offset their full consumption, but you don't necessarily want to. Some people also just want to get themselves down to a lower tier. You're going to subtract off that discounted value, the variable cost and the fixed cost of installing, and then the X beta include all of our extra controls that we've already been talking about here. We are going to simplify this expression with this theta Q star P bar term. So P bar is just that average cost of the offset electricity at the optimally sized installation. Q star is the generation from the optimally sized installation. And theta is sort of the summation term. And it's going to value between, and it's quarterly data. So it goes between 0 and 100. 100 is the maximum value you would get if you didn't discount the future at all, because there's 100 quarters for the life of your panel. 0 would be if you got no value from the offset electricity at all. So the size of theta determines how much you're offsetting that future value. And it's just a much simpler way of writing it. We're going to normalize the outside option to be 0 plus this stochastic term. Given that we're actually using the cost of electricity, that gives us our normalization. So we put the sigma here. We don't have to assume a second normalization. And then we're going to use sort of a standard CCP estimation approach to trade off the value of adopting today versus the value of adopting tomorrow. So again, this first term, this is the stream of benefits from adopting. Here we got the variable cost of installing. This is the fixed cost of installing. Here's the controls. And then here is your Euler constant. And next period's probability of adopting. It's really important to do this in a dynamic setting. We've gotten this question from people mostly in environmental economics. But you got to account for the fact that, again, if Wes has a sunnier roof than me, not only is the value of adopting today higher, he also has a greater likelihood of adopting tomorrow because he's also going to get more value from adopting tomorrow. So you have to account for the fact that PR prime will also depend on your solar irradiance through that way. So you have to do this with a dynamic model.
Hey, Brian, sorry, not to go back to my previous question, but on the previous slide, on like the slide before this one, if we think that, let's say for low wealth households, that capital T is just lower, they're just integrating over fewer periods because let's say they move more frequently, right? That would be captured in the discount rate. So I wonder if you could just show that the time that lower wealth households spend in a house are similar to higher wealth households, then that would do away with that.
Yeah, we could. I expect you're going to see, we haven't looked at the correlation. I'd be shocked if you don't find that lower wealth households have also been in their current residence a shorter period of time, especially because these are owner-occupied homes. So if you're lower wealth, chances are you haven't been able to buy a house as long ago as someone who's higher wealth. Mm-hmm. So I do expect that there to be a correlation. In terms of our ability to identify parameters, or we can identify this theta. Trying to separately identify the delta and the T would be incredibly hard.
Yeah, but I guess what I'm suggesting is like, could you use T like as data that differs across
only if you're going to make the assumption that the number of years I've been in the house is the number of years I expect to be in the house.
Yeah.
So that's my concern. I did say that it is hard for us to separately identify them. In theory, we do have 1 degree of freedom where we could identify something else if you wanted to put some more flexibility on expectations or that T term. If you look at this difference in the delta 1 minus delta 0, the discount rate appears in the theta, and this is where we want to really get our identifying power from. But you also have the rho term in front of the log PR prime term. And that's where typical papers who've estimated discount rates have really gotten a lot of identifying power. Some policy changes in the future, that affects my likelihood of adopting tomorrow because the value of adopting tomorrow has gone up or down. And that difference in PR prime, right, that variation allows me to get this rho using that term without this first term at all. We didn't want to go that route because we thought that that really relies on you getting the PR primes right? They're supposed to be non-parametrically estimated for these methods. We're also going to use a flexible logit, like a lot of papers have done for this. That's where the stronger assumptions on future expectations come in as well, with when you estimate that PR prime. So while in theory we could try to do that, we didn't want to. And we get very little variation within a household actually in PR prime because we chose a period in which policies aren't changing that much, back to Olivier's question. And we did that deliberately so we could focus the identification on this first term. The downside is that we can estimate theta, but we can't decompose it if other things are changing here. Again, for a lower wealth household, if T is expected to be less than 25 years, there's still that residual value of the solar panels on the house. So I actually wouldn't want to change T. I would just want to somehow discount the flow more, or I have a shorter T and then I have to have the value from that T to the 25-year mark on how much the buyer of the house is going to value it. And it's something that we didn't really want to go there. That said, you can argue that the reason why we see lower discount rates, or sorry, higher discount rates for lower wealth could be due to that T.
And I guess it just depends, like in the counterfactuals, maybe it doesn't quite matter from which source it's coming from. So I don't know.
For the counterfactuals we're going to do, it's not going to matter. For some counterfactuals, I think it would matter. Right? Housing policy counterfactuals, which might change how long you're going to be in the house, clearly it would matter. Financing policies, if you're going to offer lower wealth consumers better APRs for solar, which some green banks are doing, then it would matter, you know, whether discount rates are actual time preferences or costs of borrowing. So for some counterfactuals, it will matter. We're going to primarily focus on shifting NEM benefits to upfront incentives, in which case it's the implicit discount rate that we estimate that we think is the value that really matters. We'd love to decompose it more. We just don't have the identifying variation without stronger functional assumptions. It's also going to be exponential discounting. We've been asked this before as well. I don't think we want to try to move beyond this. But again, we do have one extra degree of freedom that we could work with if we wanted to. We're going to allow that discount rate to be the simple function of wealth. We're going to have bins for medium wealth and high wealth. And then really we're just testing to see whether alpha 1 and alpha 2 are different and significantly different from 0.
So Bryan, so in so the assumption, the implicit assumption a bit here is that the price sensitivity is not really varying among groups, right? So because the value functions are written in dollars, so it's not that explicit as if you would have it with like a price coefficient and an alpha in front of it or something like that. But it's basically like sigma is not income specific. So is it correct to say that if low and high income people have different price sensitivity also for upfront costs, it will now be channeled through the discounting?
That's a really great question. I don't believe we have allowed sigma, and because of our normalization, yeah, we come through on the sigma. I don't believe we've allowed sigma to be wealth specific, but I thought we might have tried that at one point. It's a great question. I think currently we are assuming a common sigma, but we can easily relax that assumption to allow for different price elasticity. The estimation challenges, I mentioned the PR prime is important to get right. We just can't subsume this into the intercept for the reasons I already said, because someone with more sunlight has a higher probability of adopting tomorrow as well. So we're going to use a flexible logit model for that. We also have the challenge that a lot of adopters, or not a lot, a reasonable fraction of them are leasing their system, which actually means that it's not necessarily an upfront payment that they have to pay. There are 0 upfront lease systems, so we're going to have to write down a reasonable price for lease systems as well. We go with the model in which installers demand a reasonable rate of return that we can estimate as a function of that upfront price. And then the last issue, of course, is the fact that we don't actually see consumption for non-adopters. We just know what the profile of consumption is within a zip code. I think I only have 7 minutes, so I should probably go over some of these challenges quick. I mentioned that we're going to estimate this logit to get the PR prime in a flexible way. In terms of the lease systems, we're going to assume that each household has a permanent unobserved state as sort of a lease or a purchase type person. We don't really believe in the data that people are going to switch which one they would prefer. We tried a model in which we had people optimally choose to lease or choose to purchase, but the data just don't look that way at all. You get some people who lease who really should purchase their systems, and some people who purchase who really should lease. So we went with this time invariant heterogeneity. So we'll have to put a caveat on that. Any drastic change in the environment in which someone might want to become a leaser who's a purchaser, that's something that our model is not currently capturing. We're going to write our model conditional on this unobserved type as well as on the unobserved consumption bin. For leasers, we're going to incorporate a payment to the lessor. We're going to allow for this fixed markup term. We're also going to allow for a per kilowatt hour markup term, and the results are sort of similar either way. For the installer's discount rate, we're going to assume a 4% discount rate. For estimation, conditional on your parameters B, your consumption bin, and E, your leaser type, we can calculate the probability of adopting and the conditional likelihood of adopting conditional on being in that bin. So there's 10 unobserved states, 5 consumption bins, and 2 lease types. The integration, again, is quite a bit more complicated than standard Cedar and Miller, because of the fact that if you give me a nice, a high consumption profile, that lessens the likelihood that other people in my zip code have a high consumption profile. So the integration can't be at the household level. It actually has to be at the zip code level where we have the empirical distribution of consumption. So it just adds this extra complication. The method is the same as A&M. We're going to calculate weights for each type conditional on this ratio of likelihoods. Again, this is straight out of our Cedar and Miller. But these likelihoods are not going to be household specific likelihoods, but zip code specific likelihoods, conditional on a draw of allocations. So think of it like I see every household's consumption in the zip. I'm going to randomly draw. Wes gets this one, Christina gets this one, Raluca gets this one, and do this for many, many draws. In terms of our results, when we estimate this, without heterogeneity, we get an average discount rate of just under 14%, very similar to Olivier's 15% that they got. It was Germany. Like, it wasn't Germany, right?
It was Belgium.
Belgium, thank you. Okay, so very similar to that. The net present value of future payments with this discount rate is about $9,000. At the government's discount rate that we set to 4%, it would be $20,000. So the per period payoff is 2.2 times higher with the government rate than the consumer rate. So consumers just don't value the stream of benefits the same way we would expect the government to do. This suggests that there could be efficiency improvements by moving some of these incentives up front. When you look at the difference across wealth bin, we estimate discount rates of 19.8% for low wealth and about 10% for high and medium wealth. And if you want to look at the ratio of high to low, through the theta, again, I told you 100 is the maximum theta with 0 discounting. We see a 1.8 ratio for high to low wealth. This means that high wealth consumers value the stream of benefits 80% more than low wealth consumers. So not only are there efficiency gains to be had from moving the upfront incentive or moving the NEM benefit to the upfront incentive, there's going to be distributional implications as well, where we should expect to see lower wealth consumers adopting solar. And those are the counterfactuals we're going to do. I don't have a lot of time. This first counterfactual is just what would happen if we reduced upfront costs by 1%. This is to give us an idea of elasticities. Elasticities vary between 0.9% and 2.6%. You see more elastic high consumption or high wealth consumers. And then the ones that we really want to get to are things like changing the NEM to a different cost. The current policy being considered is a 6.25 cents per kilowatt hour policy in California. This would be export electricity. So when you're generating electricity as you consume it, right, you don't have to consume from the grid at all. So you still get a value equal to your current marginal rate. But when you're over generating during the sunny periods of the day, the value would be 6.25 cents. So the total benefit of solar would decline, the flow benefit, and that's the counterfactual we're working on right now. And if you see this decline, high wealth consumers, only 22% of them would have installed, whereas almost 60% of the low wealth consumers still would have installed, because again, they were valuing that stream of benefits at a much lower rate than the high wealth consumers. So I only have a minute left. We're going to do another counterfactual in which we combine the reduced export compensation with an upfront subsidy. We have to do some of the robustness checks that already came up today. And again, in conclusion, we find discount rates of about 14%, greatly exceeds the government borrowing rate, implies efficiency gains. Our main results really, I think, are the heterogeneity in discount rates that we find across wealth bins, which can at least partially explain this big disparity in the wealth across adopters. And that is it. One on the dot, right? thank you all for your time, and I look forward to getting feedback.